first problem பார்த்தீங்கன்னா that is the R of x is a commutative ring with unit. எப்போ this is the R of x is a commutative ring with unit whenever R is a commutative ring with unit. So R be a commutative ring with unit element. Now R of x is obviously commutative ring with the unit element. So easily we can verify that is f of x equal to summation of ai xi because of this polynomial, okay, with real entries. So the g of x is also like this. The ai bi la real entries are இருக்கும். So summation bi x power I. Then the sum பண்ணும்பொழுது உங்களுக்கு real entries add பண்ணுவோம். So ai bi belongs to R என்றதுனால ai plus bi is also belongs to R. So அதனால obviously belongs to R of x. So like that we can easily prove that R of x is a commutative ring with unit. So the same way for the associativity and additive identity is 0. The 0 polynomial we can express very simply. The 0 என்றது 0 polynomial in R of x என்றதுனால. So 0 polynomial 0 plus 0x 0x square and so on. So as the additive identity. And the additive inverse பார்த்தீங்கன்னா negative of the polynomial is the additive inverse. And commutative பற்றி பார்த்தீங்கன்னா obviously true because of the polynomial f of x plus g of x is always g of x plus f of x. And closure for the multiplication பார்த்தீங்கன்னா f of x into g of x is obviously belongs to the R of x because of the ai bi is ai is belongs to R என்றதுனால. And associativity is always true and distributive law is always true because of the distributive law is true for R என்றதுனால the corresponding polynomial is always true. Multiplicative identity is the one is we can express 1 plus 0x 0x square and so on serve as the multiplicative identity. And the commutative property for that f of x into g of x is always equivalent to g of x into f of x. So in the polynomial function, so this is a R of x is a commutative ring with unit element. With unit element if whenever R is a commutative ring with unit element. R is a commutative ring with unit element na R of x into the commutative ring with unit element அப்படின்னு சொல்லலாம். The same way this is the another result R of x1 x2 xn R of xi1 xi2 xin. The I1 I2 in என்றது என்ன அப்படின்னு பார்த்தீங்கன்னா that is a permutation of 1 to n. The permutation of 1 to n. Okay, well this is the maybe important one. I thought இது ஒரு competitive exam பார்த்த மாதிரி இருக்கு. So this is the R of xi1 xi2 xin என்றது this is equivalent to R x1 x2 xn. In the case of I1 I2 in என்றது is a permutation of 1 to n. So it's easily proved by the induction, mathematical induction concept. And another one is also very important. R is an integral domain. R is an integral domain. Then R is an integral domain. Then f of x belongs to f of x g of x in R of x. Then degree of f of x g of x we can express degree of f of x plus degree of g of x. Degree of f of x plus degree of g of x. Let's be that is f of x equal to something mth degree polynomial. The highest coefficient, highest power, the coefficient of the highest power should be not equal to 0 because of this is considered as the mth degree polynomial. அதே மாதிரி g of x is the nth degree polynomial with the condition b of bn is not equal to 0 because of in the case of bn equal to 0 this is cannot be a degree m. So ரெண்டுத்தினுடைய degree வந்து பார்த்தீங்கன்னா degree of f of x m, degree of g of x equal to n. So அதனால தான் இந்த condition am is not equal to 0, bn not equal to 0 என்றது. ரெண்டுத்தையும் ப்ராடக்ட் பண்ணிங்கன்னா like this இது மாதிரி ஸ்ட்ரக்சர் கிடைக்கும், that is the m plus n. So the degree of f of x into g of x m plus n. m என்றது degree of f of x, n என்றது degree of g of x. It's very easiest to prove. The same way R is an integral domain with unit element. R is an integral domain with unit element. Then any unit in R of x must already be unit in R. Already be unit in R. So what is the unit element? Unit element f of x belongs to R of x is a unit. அப்படின்னா there exists the another function g of x, the product of these two functions should be equal to 1 இல்லையா? that is the unit element உன்னுடைய definition. so the degree of f of x நமக்கு தெரியும், degree of f of x plus degree of g of x. so degree of f of x into g of x, that is called the degree of 1. degree of 1 என்றது 0. அப்படின்னா நமக்கு என்ன கிடைக்குதுன்னா RBN integral domain, that is degree of f of x plus degree of g of x equal to 0 னு வந்துருது இல்லையா? so degree of f of x plus degree of g of x equal to 0 னா then degree of non-negative integer, that is degree of f of x and degree of g of x, both of them equal to 0. and f of x, g of x both are should be the constant polynomial, that is f of x equal to e, g of x equal to b, then only degree of f of x plus degree of g of x equal to 0. with a comma b belongs to R, then a comma b belongs to R, na, that is should be a into b equal to 1, because of a is a unit, so a is a unit in R. because of degree of f of x equal to, that is the constant, both are constant na, that is namakku degree of f of x, g of x equal to 1 na. so that is therefore with a comma b belongs to R என்றதுனால, so that means ab should be equal to 1. ab equal to 1 na, that is a is unit or b, a is a unit in R, a is a unit in R, that is the idea. so that means degree of R of x is a unit, R of x must already be unit in R, already be unit in R. in the case of R is an integral domain with unit element, any unit in R of x must already be unit R, any unit in R of x must be already in unit in R, units in the polynomial range. the zero devices, zero devices in the polynomial rings, zero devices 9 and 3. okay, well, so R be a commutative ring with no non-zero nilpotent elements, with no non-zero nilpotent elements, the f of x equal to something m degree polynomial in R of x is a zero divisor. that is there is an element b is not equal to 0 in R, must be ba0, ba1, bam equal to 0. so that is the zero divisor in the polynomial ring. so zero divisor in the polynomial ring means there exists some polynomial, that polynomial in R of x is a zero divisor now, there is some non-zero element in R, that non-zero element product with the coefficients of the polynomial should be equal to 0. coefficient of the polynomial should be equal to 0. general zero divisor ரெண்டு non-zero element multiply பண்ணா 0 வந்ததுனா, that is called the zero divisor, that is the zero divisor. so that is inge f of x is a zero divisor. okay, then there exists the non-zero polynomial, another non-zero polynomial g of x, the product of should be equal to 0. அப்படின்னா g of x ஒரு n டிகிரி polynomial நாம் எடுத்துக்கிறோம். அப்படின்னா இது ரெண்டுத்தினுடைய ப்ராடக்ட் all such non-zero polynomials g of x, that is f of x into g of x equal to 0, choose one of the minimal degree n, that is the bn be its leading coefficients. leading coefficient means the highest power coefficient. then bn f of x equal to 0, bn f of x equal to 0, that means this is true. so then taking b equal to bn is not equal to 0. so that is degree of f of x equal to n, so bn ai equal to 0 for all I, bn is not equal to 0 element. suppose for the contradiction bn f of x is not equal to 0, then bn f of x is a non-zero polynomial Since f of x into g of x equal to 0, the product obviously in the form of like this a naught b naught b1 plus a1 b naught like this. இது மாதிரி மல்டி பண்ணுவோம் ரெண்டு பாலினாமியல. So in the coefficient of x power m plus n, am bn should be equal to 0. So consider the polynomial h of x equal to bn g of x minus bn x power n into f of x. So the polynomial degree less than, this is the polynomial degree less than n, since x power n terms is cancelled, that is in the case of a bn equal to 0. So therefore f of x into h of x equal to look like this f of x into bn g of x minus bn x power n f of x. So this is the f of x whole square. So this is 0 minus 0, this is equal to 0 because of this is the bn f of x g of x equal to 0 என்றதனால f of x whole square is 0. So h of x is a non-zero polynomial and bn g of x is not equal to 0, bn x power n f of x has a different degree or 0 of degree less than n with h of x, f of x into h of x is equal to 0. This is a contradicts of the minimal polynomiality of n, minimal polynomiality of n. Therefore bn f of x should be not equal to 0. Our assumption bn f of x is not equal to 0 must be false. So bn f of x should be equal to 0. So which is means bn ai equal to 0. So for every I equal to 1, that is the proof. That is the proof. And zero divisor na ஏதாவது ஒரு non-zero element in R ல அந்த coefficients கூட multiply பண்ணா that is equal to 0 வரும். Okay, that is the definition for the zero divisor in the polynomial rings. நமக்கு general definition ரெண்டு non-zero elements வந்து product பண்ணா 0 வரும். That is definition is also exist in the polynomial rings. Polynomial rings like that, f of x is a zero divisor. Then we can derive this new definition for every non-zero divisor of the polynomial. There exists some non-zero element, that is product with the each and every coefficient should be equal to 0. That is a zero divisor without nilpotent condition. So previous problem nilpotent condition வந்திருக்கும். That is the characterization of the units in in R of x, and R be a commutative ring with unit element. Then f of x is the nth degree polynomial in R of x is a unit. This f of x is a unit if and only if, what is the condition, a naught is unit in R and a1, a2, an are nilpotent elements in R, Okay, so this is a very important one of the result, that is the characterization of the units in R of x. So some polynomial is unit now, that is the constant term of the polynomial should be unit in R, and other coefficients are nilpotent element in R. Other elements are nilpotent element in R. So that means, what do you mean the nilpotent element? So the element power something, there exists some positive integer that should be equal to 0. So a naught, that is first of all a naught is unit, a1, a2, an are nilpotent. Then I will try to prove f of x with coefficients a0, a1, an is unit in R of x, So the a0 is unit, okay. So there is another element, that is product is equal to 1. And this is a nilpotent, means then each I greater than equal to 1 is nilpotent. So that means there exists some capital N such that ai power n equal to 0 for all I greater than equal to 1. So there exists consider the polynomial g of x, look like A naught inverse, because of why A naught inverse, that is A naught into some element equal to 1, that is that expresses some A naught inverse into 1 minus h of x plus h of x square plus minus h of x whole cube plus and so on. What is the A naught h of x? H of x here is in the form of minus A naught inverse into a1x and so on an x power n. So since h of x is a nilpotent, why h of x is a nilpotent? The sum of as sum of nilpotents in a commutative ring, sum of nilpotent is a commutative ring, so this is the nilpotent. a1 a2 an are nilpotent. Each and every one is a nilpotent, so that is h of x is nilpotent. The series terminates, so f of x into g of x equal to f of x into g of x. This is the g of x. So f of x into g of x, f of x is already defined, so the product should be equal to 1. Product should be equal to 1. So that is the idea. That is from this f of x is a unit. F of x is a unit. When you specify we can write like this: ai is nilpotent, h of x is nilpotent in R of x. 1 minus h of x is unit in R of x. 1 minus h of x is unit in R of x. So therefore, unit in R of x with inverse 1 plus h of x to h of x whole power n. The same proof once again. Then f of x equal to in the form of a naught 1 minus h of x. So from the definition of the f of x, so f of x whole inverse equal to the something 1 minus h of x whole inverse a naught inverse. So this is implies since f of suppose this is implies f of x into something f of x whole inverse that is equal to 1. So suppose the f of x is unit in R of x, then there exists a g of x equal to b naught b1x and so on bm x power m such that f of x and g of x equal to 1, that is given. This is the contradiction part. So there is f of x, g of x equal to f of x is unit in R of x. I will try to prove the a naught is a unit and other coefficients should be nilpotent. So the comparing the coefficient a naught to b naught should be equal to 1. Should be equal to 1. So a naught is a unit, that is okay. A naught b1 plus a1 b naught equal to 0 and a naught b2 other coefficients are should be equal to 0. Other coefficients are should be f of x g of x equal to 1 in which term. From that a naught b naught equal to 1. The other coefficients are should be equal to 0. So by the induction that a k power m plus 1 equal to 0 for every k greater than equal to 1. So therefore a naught a1 b1 when you substitute here and a1 square b naught okay a1 square b naught, this is equivalent to multiply the second equation by a1. This is equivalent to a1 square b naught equal to minus a naught a1 b1. So from the first equation, that is b naught equal to a naught inverse and minus a naught inverse a naught b naught plus and so on. And containing this process, this is a1 is nilpotent. A1 is, that is continuing this process, that is b naught equal to like this from the first equation, a naught inverse. So like this, therefore a1 is nilpotent. A1 is nilpotent. Okay. So therefore the same idea. So consider the ideal, that is ideal I equal to generated by a1 that is model. So we can leave it to this idea. So the same way f of x1 x2 is not a principal ideal. F of x1 x2 is not a principal ideal ring. So that means when f is a field, f of x1 x2 is not a principal ideal ring. So the ideal means that is generated by some elements that is called the ideal. So in f of x1 x2, suppose for the contradiction I is a principal ideal. So that means I equal to generated by f of x1 x2 for some f belongs to f of x1 x2. So x1 belongs to I, then x1 is expressed as f of x1 x2 g of x1 x2, g is belongs to f of x1 x2. That is the principal ideal. So taking the degree in x1 is 1. இதனுடைய degree பார்த்தீங்கன்னா degree of fg equal to degree of f plus degree of g over x1. Okay, degree of the in over x1 is 1 equal to degree of f over x1, degree of g over x1, because of the two variables are there, ரெண்டு variable இருக்கிறதுனால. So degree of f over x1 equal to 0, degree of g over x1 equal to 1. That is, this is implies இதுவாக இருக்கலாம், இது 1ஆக இருக்கலாம், இது 0ஆக இருக்கலாம், இல்லை இது 1ஆக இருக்கலாம், இது 0ஆக இருக்கலாம். So the same way x2 belongs to I எடுக்கிறேன். x2 equal to the product of f of x1 x2 h of x1 x2. So the degree pattern must be consistent the same way. So f must be divided the both x1 and x2. The only monomials dividing x1, only monomials dividing x1 are 1 and x1, and the only monomials dividing x2 are 1 and x2. So the only common divisor is 1. Abna f, but if f equal to 1, I is generated by 1 in, that is equal to f of x1 x2, which is a false because of the constant polynomial or not in I. Constant polynomial I inter ideal la irukadu, principal ideal la irukadu. So I is not a principal ideal. So therefore I is not a principal ideal na f of x1 x2 is not a principal ideal. So it's a very simple proof, very important concept. And another lemma, R be a unique factorization domain, a comma b belongs to R, then a and b have the greatest common divisor. R into the unique factorization domain aranda, a and b have the greatest common divisor, a comma b in R. If a comma b equal to 1, that is a and b are relatively prime, that is a comma b equal to 1, then and a divides bc, then a divides c. This is நிறைய தடவை பார்த்துருக்கோம். This is the under the condition unique factorization domain. This is also very simple, very important result. A belongs to R is irreducible element. A divides BC, then A divides B or A divides C. And content na ennu paarthom already, the content and primitive decomposition. So that means R be a unique factorization domain. Every f of x belongs to R of x can be written as a into f1 of x, where a belongs to R, f1 of x is primitive. f1 of x is a primitive. So primitive means the coefficients of the polynomial should be equal to GCD of the coefficient of the polynomial should be equal to 1. That is the primitive. So the decomposition in part A is unique. It is unique R. That is the second idea. The case of R is a unique factorization domain. Okay, that every polynomial can be expressed in the form of a into f1 of x. A is belongs to R, f1 of x is primitive. That A should be is called the content of the f of x, content of the f of x. So it's a very simple proof. Here f of x is belongs to R of x. A equal to GCD of the coefficients. Okay, that is called the content of f of x. and AI equal to ABI, AI equal to ABI. Am I correct? For each I, G3 of B0, B1, B2, Bn equal to 1. Then f of x equal to A into the bi a equal to abi in eduthuko. So that is the bi than the coefficients b0, b1, b2, bn. So this is f of x, obviously correct, because of bi equal to ai by a என்றதனால this is equal to f of x. So this is called f1 of x. That f1 of x is a primitive by the construction of the function. F1 of x is the primitive. Okay, that is the proof. The same way, a equal to f of x equal to a into f1 of x, that is b equal to g1 of x. Then a comma b belongs to R. F1 of g1 of x are primitive. So the coefficients ai of f of x, a equal to a, and b for the coefficients of g1, f1 of x, g1 of x are primitive. A and must be associate இருக்கணும். Associate means that is they both are the G3 of the coefficients of f of x, that is a and b. So the content of f is a, content of f1 equal to a. So that because of f1 is primitive, similarly content of f equal to b, content of g1 equal to b, then must be a equal to b up to units. So therefore a f1 of x, a g1 of x both are equal. Now that means f1 of x equal to g1 of x. So the decomposition is unique. Decomposition is unique up to the associations. Another representation, R is an integral domain. R is an integral domain. F is its field of quotients. Any element f of x in f of x can be written as f of x equal to f naught of x by a. F naught of x belongs to R of x, a is belongs to R. So integral, R is an integral domain, f into the field of quotient, any polynomial in f of x we can express in the rational form f naught of x divided by a. F naught of x into the R of x. That is the idea. Okay. So that is f of x equal to something polynomial. So f is the field of quotient. F is the field of quotient. Each and every coefficient we can express in the field of fraction. The quotient means that is a naught by ba in eduthalam. That is ai by ba in eduthalam. Ai ba belongs to all, ba not equal to 0. So a equal to a b naught b1 bn, the product of all denominators, and then for each a, aci equal to a into ai by ba, that is a into the b0, b1, b2, bn, am I correct, divided by ba into ai, belongs to R, obviously belongs to R. Ba divides the product of b0, b1, bn. So now define the f naught of x like that, a into f of x. Then each coefficient ACI should be belongs to R. Each ACI is belongs to R. Therefore, f naught of x belongs to R of x. Therefore, f of x equal to f naught of x divided by a. F naught of x belongs to R of x. A belongs to R. The converse of the lemma is if the primitive polynomial f of x belongs to R of x is irreducible as an element of f of x, so then it is irreducible as an element of R of x. So that means if the primitive polynomial f of x, primitive polynomial f of x in R of x is irreducible. Irreducible na factorize பண்ண முடியாது அப்படினு அர்த்தம், because of the coefficients of the f of x is G3 of the coefficient of f of x வந்து 1. Okay, irreducible of f of x இருந்ததுன்னா then it is irreducible in R of x ன்னு சொல்லலாம். R of x ல irreducible சொல்லலாம். Okay, that is f is the field of fraction of R. Field of fraction of R. Irreducible na factorize பண்ண முடியலன்னு அர்த்தம். அப்படியே தான் இருக்கும், factorize பண்ண முடியலன்னு அர்த்தம். அதே மாதிரி this is the f is the field, then f of x1 x2 xn is a unique factorization domain. f into the field இருந்ததுன்னா then f of x1 x2 xn is a unique factorization domain. Unique factorize பண்ண முடியும். That is the idea. That is the principal ideal rings or unique factorization domain. Principal ideal rings is a unique factorization domain. Already பார்த்துட்டோம் நினைக்கிறேன். This is very important. And z of x1 x2 xn is a unique factorization domain. If a J is a ring of integers, J of x1 x2 xn is a unique factorization domain. Okay, J is the ring of integer now. So it's a for the n equal to induction la prove பண்ணிருக்காங்க. That is the n equal to 0 na J equal to z ஆயிடும். இல்லையா? is a unique factorization domain. Fundamental theorem of arithmetic. Okay, J equal to z na any integer. So that means assume that z of x1 x2 xk minus 1 is a unique factorization domain. So then I will try to prove the z of x1 x2 xk is a unique factorization domain. So how to express this one? Z of x1 x2 xk minus 1 into xk. So already namakku idu unique factorization domain theriyum. It's a polynomial rings in one variable is also unique factorization domain theriyum. ரொம்ப முக்கியமான பாயிண்ட். polynomial rings in one variable is also unique factorization domain. ரெண்டுத்தினுடைய ப்ராடக்ட் இஸ் a unique factorization domain. அப்படின்னா z of x1 x2 xn என்றது is a unique factorization domain for every n greater than equal to 0. So fundamental theorem of polynomial rings over unique factorization domain என்னன்னா R is a unique factorization domain இருந்தா R of x என்றது unique factorization domain, R of x1 x2 xn என்றது unique factorization domain. The irreducible elements in R of x are either irreducible elements of R or primitive polynomials that are irreducible in f of x, not R of x, in f of x. So f is the field of fraction R. F is the field of fraction R. Okay, this is a very important result. The same way unique factorization domain, that is z of x1 x2 xn multivariate polynomial over integers, this is the unique factorization domain. F of x1 x2 xn is a multivariate polynomial over a field is a unique factorization domain. Z of root d, square root of d, okay, that is of the polynomial x1 x2 xn is a unique factorization domain. So units in polynomial rings, R is a commutative ring with unit, then f of x belongs to R of x is a unit அப்படின்னா a0 is unit in R இருக்கணும், a1 a2 a என்றது nilpotent elements in R இருக்கணும். Already பார்த்தோம்னு நினைக்கிறேன் இந்த ரிசல்ட். These are some problems. Okay, R be a commutative ring, an ideal P of R is said to be prime ideal, is said to be prime ideal of R if AB belongs to P, A comma B belongs to R. It implies that A belongs to P, or B belongs to P. Okay, but then prove that P is a prime ideal of R if and only if R by P is an integral domain. P is a prime ideal of R if only if R by P is an integral domain. So the first part that is the pi from R to R by P is the projection pi of A equal to A plus B. Am I correct? This is called the canonical projection. That is pi of A equal to R by P element is of the form A plus B. Suppose P is prime that is a P is a prime ideal R is a commutative ring as a unit or as a 1, then R by P is also unit element 1. So in place that is R by P is a commutative ring with unit element 1. So that is a zero divisor condition check A plus P B plus P is equal to ready to multiply that is AB plus P AB that is equal to 0, that is AB plus P, that is equal to 0 plus P. So this means AB plus P equal to P. That means AB belongs to P. AB belongs to P. Since P is a prime, A belongs to P or B belongs to P. Apna A plus P equal to 0 plus P or B plus P equal to 0 plus P. Therefore, R by P has a no zero divisor. R by P has a no zero divisor. Okay, so P is a, so that means R by P is a no zero divisor. No? That means that R by P is an integral domain. R by P is an integral domain. So that is the idea. And converse part, R by P is an integral domain now. So that means let AB belongs to P, that is given, and pi of AB equal to, we can express 0 plus P, pi of AB equal to 0 plus P, because of this the prime, so that A plus P, B plus P equal to 0 plus P. So since R by P is an integral domain, either A plus P or B plus P equal to 0 plus P. So that is A belongs to P or B belongs to P. So that from this, what is the conclusion? That is P is a prime. P is a prime. And R is a commutative ring with unit element, that every maximal ideal of R is a prime ideal. In the case of the commutative ring with unit element, every maximal ideal is a prime ideal. That is, M is the maximal ideal means this is the maximal ideal generated by something. So already we know that R by M is a field because of M is the maximal ideal. So with unit element, so every fields are integral domains. Fields are integral domains. So which is implies M is prime. M is prime because I've already proved for the integral domain the ideal is the prime ideal. For the integral domain, ideal is the prime ideal. So that is the R by M is the field means R by M is an integral domain. R by M is integral domain means M is the prime ideal. M is the prime ideal. Okay, weights may be important. And given an example of the ring with some prime ideal, not a maximal ideal. So which is the good example? R equal to Z is a ring of integers. How to define the ideal? P equal to 0 is called the prime because of Z is an integral domain. Z is an integral domain. So but 0 is not a maximal ideal because of, since Z by 0 is not isomorphic to Z, is not a field. That is the one of the method. Z by 0 is not a field, so 0 is not a maximal ideal. So therefore P equal to 0 is a subset of generated by 2. Okay, but this is the subset of generated by is Z, that is the 2 is the prime number. So 0 is not a maximal. 0 is not a maximal. 0 ன்றது மேக்ஸிமலாக இருக்குன்னா 0 தான் இருக்கிறதுலே பெரிய ஐடியலாக இருக்கும். ஆனால் இங்கே 0 விட 2 is the பெரிய ஐடியல். So that is not a maximal. Okay. So the prime ideal exists, some prime ideal that is not a maximal ideal. That is not a maximal ideal. Another example பார்த்தீங்கன்னா R equal to Z of X. P equal to the prime ideal is generated by some element X. Then R by P is isomorphic to Z, is an integral domain. R by P is isomorphic to Z, that is P is generated by some arbitrary element X. So is an integral domain but not a field. So therefore P is a prime, not a maximal ideal, not a maximal ideal. R is a commutative, R is a finite commutative ring. Finite commutative ring. That means that ring has only the finite number of elements, or as only finite number of elements. with unit element. R is a finite commutative ring with unit element. So then every prime ideal of R is maximal ideal. This is a mukkiyamaana result. Okay. So that every prime ideal of R is a maximal ideal of R. Suppose P is a prime ideal of R. R by P is an integral domain. By the problem 1 என்ன சொல்றதுனா R is a finite. R is a finite என்றதுனால R by P is a finite. நமக்கு என்ன தெரியும்? Finite integral domain is a field ன்னு தெரியும். Every finite integral domain is a field na. So R by P is a field ஆயிடும். R by P is field ஆயிடுச்சுனா P is a maximal ஆயிடும். So very simple proof, very important result. In the commutative finite commutative ring with unit element, every prime ideal of R is a maximal ideal of R. And another one pathina F is a field, then f of x is isomorphic to f of t. F of x is isomorphic to f of t. Suppose define the function f of x to f of t. F of x is the polynomial, collection of polynomials. So a collection of nth degree polynomial is equivalent to, that is the nth degree polynomial in terms of t. So this is well defined, and respect to addition and multiplication, it just changes the intermediate symbol x to t, that is the idea. Obviously pi is bijective, that is 1 to 1 on 2 are there, and pi of 1 equal to 1. Pi of 1 எடுத்தீங்கன்னா 1 ன்னு வந்துரும். So pi is isomorphism of rings. Pi is isomorphism of rings. The case of f is a field. And all automorphism sigma of f of x. All the automorphism sigma of f of x with the property sigma of f equal to f for every f belongs to f. Okay, so sigma being an automorphism, the collection is ax plus b. Ax plus b. Okay, well, it's a very simple thing. This is a collection of all automorphisms. And another one, R is a commutative ring. R be a commutative ring, n equal to x belongs to R, x power n equal to 0 for some integer n. Here n is an ideal of R, n is an ideal of R, and integral domain, that is in R la vandu R by n, in R equal to R by n, the x bar of m equal to x bar power m equal to 0 for m some m, then x bar equal to 0. X bar equal to 0. So that is n is the collection of elements from R with the condition x power n equal to 0 for some integer n. I will try to prove the n is an ideal of R. N is an ideal of R. Ideal definition I am already telling, that is familiar. So obviously 0 belongs to n because of 0 power n equal to 0. If you take the x comma y belongs to n, x power n equal to 0, y power m equal to 0 for some integer m for some integer n, that is n comma m greater than 0. The first one, the closure, the x plus y whole power n plus n minus 1. By the binomial theorem expansion, this is each term is of the form like that. Binomial theorem expand பண்ணீங்கன்னா, if k is greater than equal to n, x power k equal to 0. If k is less than n, okay, if k is less than n, then n plus m minus 1 minus k should be greater than m minus 1, that is n plus 1 minus k greater than equal to m, or y power something equal to 0. So each term is 0, so hence this is equal to 0. Now x plus y belongs to n. But next in R is belongs to R, x belongs to n, that is Rx is equal to Rx belongs to n and சொல்லணும். X belongs to n, x power n equal to 0. R is belongs to R, so Rx plus whole power n கண்டுபிடிக்கிறேன். So R power n x power n எடுக்கலாம். X power n 0, அதனால this is equal to 0. So Rx power n equal to 0 na Rx என்றது n ல இருக்கும். So n is an ideal. The same way x bar whole power r bar, that is belongs to r power r, with the x bar whole power m equal to 0. X power m belongs to n, that is there is exist k such that x power m whole power k equal to 0. So x power mk equal to 0, x belongs to n and x bar equal to 0. The same way R is a commutative ring. Suppose A is an ideal of R, A is an ideal of R. Let n of A equal to x belongs to R, x power n belongs to A for some n. So that is n of A is an ideal of R, n of A is an ideal of R which contains A. n of A equal to n of A into n of A. n of A என்றது defined like that. முன்னாடி வந்து equal to 0 கொடுத்திருந்தாங்க. இங்கே x power n belongs to A for some n. That is idea. A என்றது ideal. A is an ideal of R. Then n of A is an ideal of R which contains A. n of A equal to n of A into n of A. That is called radical of A அப்படின்னு சொல்லுவாங்க. Radical of A ன்னு சொல்லுவாங்க. And another result பார்த்தீங்கன்னா n is an integer. N is an integer and let Jn be the ring of integers. Jn be the ring of integers modulo n. The Kaplan is described like that. How to describe Kaplan is x modulo n and x modulo n whole power k equal to 0, congruent to 0 modulo n for some k. That is the Kaplan definition for Jn in terms of n. Okay, well this is that. Here I will try to prove this. N is the ideal. N is the ideal generated by some elements. So that is the definition. This means n divides x power k. N equal to prime factorization. N divides x power k. So that means divisible by p1, p2, pr. And that is x congruent to 0 modulus or something. So n consists of multiples of radical of n. Radical of n, product of distinct primes, dividing by n, modulo n. That is n is the ideal generated by p1, p2, pr in Z. Okay. And another result பார்த்தீங்கன்னா A and B are ideals of ring R. Then A intersection B equal to 0. Then A belongs to A, B belongs to B, AB equal to 0. Okay, AB equal to 0. In the case of the AB ideals, A intersection B equal to 0. Okay, both are A and B are ideals. So AB belongs to A because of A is an ideal, and A belongs to A and B belongs to R, AB belongs to B. Okay, because of B is an ideal and B belongs to B and A belongs to R, that is AB belongs to A test means சொல்லலாம், that is equal to 0. That is AB equal to 0 னு வந்துருது. AB equal to 0, this is the proof. Okay, R is a ring. Z of R is defined as a collection of the elements of R that is satisfying the xy equal to yx for every y belongs to R. Then Z of R is a subring of R. I'll leave it. Only polynomial rings base பண்ணி வர்றத நல்லா ஸ்ட்ராங்கா பாருங்க. Okay, polynomial rings is a very important role. அதே மாதிரி R is a division ring. Then Z of R is a field. Z of R is a field. Already proved the Z of R is a subring. And find a polynomial of degree 3 irreducible over the ring of integers. Ring of integer here denoted as J3 modulo 3. So use it to construct the field having 27 elements. So over Z3 means that is 0, 1, 2. That is the Z3. And the P of x equal to x cube plus 2x plus 1. That is a degree 3 polynomial that is irreducible over Z3. Okay, because of P of 0 not equal to 0, P of 1 not equal to 0, and P of 2 not equal to 0 over modulo Z3. degree 3 and no roots in Z3, so it is irreducible. Okay, when the 4 congruent to 1, the modulo 3 integral 1. 0 1 that is called the reducible. So k equal to Z3 of x divided by x cube plus 2x plus 1 into the field. Another field. So each element of the form எப்படி இருக்கும் அப்படினு பாத்தீங்கன்னா a0 plus a1 alpha a2 alpha square. So that is where alpha cube 2 alpha plus 1 equal to 0. Okay, and ai belongs to z3. So இது மொத்தம் எத்தனை எலிமெண்ட்னா கீழே டிகிரி வந்து 3 ன்றதனால 3 cube இது z3x field, that is 3 cube equal to 27 such element இருக்கும். So k is a field with 27 element. So very simple, already discuss பண்ணியிருக்கோம். டிஆர்பியில் இது மாதிரி ரொம்ப சிம்பிளாக தான் கேட்பாங்க. மோஸ்ட்லி நீங்கள் கிளாஸ் கவனிச்சிருந்தீங்கன்னாவே டெஃபினட்டாக மைண்டுக்குள்ளே ஏறி இருக்கும்னு நம்புகிறேன். So construct a field having the 625 elements. So that is p power n elements with p prime, that is 625 na, that is 5 power 4. So we want to field of order 5 power 4, field of order 5 power 4. Okay, that is field of order 5 power 4, f5 equal to z5. We need a monic irreducible polynomial of degree 4 over f5. So apna q of x equal to எப்படி இருக்கும் x power 4 plus x plus 1. இது எப்படி கன்ஸ்ட்ரக்ட் பண்ணணும், that is z5 னா 0 அதை போட்டுக்கலாம் 0 1 2 3 4. So q of 0, q of 1, q of 2, q of 3 and q of 4 எல்லாம் not equal to 0 இருக்கலாம். That is the monic irreducible polynomial. Okay, this is the 17 remainder 0 the modulo 5 அதனால இங்கே 0 வந்துருக்கு. 0 வந்ததுன்னா this is the root. This is the root na x minus 3 divides q of x. அப்படின்னா q of x is reducible. இது reducible. So I will try x power 4 plus x square plus 2. So like this. நீங்கள் ட்ரை பண்ணுற அளவுக்குலாம் ஆப்ஷன்லாம் இருக்காது. 4 ஆப்ஷன் கொடுத்துருப்பாங்க. அந்த 4 ஆப்ஷனில் நீங்கள் செக் பண்ணிங்கன்னா போதும். ஸோ இங்கே x power 4 plus x square plus 2 கொடுத்துருக்காங்க. ஸோ q of 0ன்றது 2 வருது. இதெல்லாம் செக் பண்ணும்பொழுது உங்களுக்கு எங்கேயுமே 0 வருதா, வரல. q of 4 வரலையும். அப்படின்னா this is one of the irreducible polynomial. So the corresponding elements பார்த்தீங்கன்னா f5x divided by q of x. f5x divided by q of x is a field with 5 power 4 equal to 625 elements. 5 power 4 equal to 625 elements. And f is a field with p of x belongs to q of x, and that is the r equal to f of x divided by p of x generated by p of x, and n is 0 if and only if that is this is n. Okay, so p of x is not divisible by the square of any polynomial. This is what about the n? N is called nil radical of r. Nil radical of r. So assume for contradiction, let's leave it. And another one, this is a very important one. The polynomial of the form f of x equal to 1 plus x cube x power 4 is not irreducible over any field f. Is not irreducible over any field f. Okay, that means f of x is by a grouping or that is f of x equal to x power 4 plus x cube plus x plus 1. இதில் x cube காமனாக எடுத்திங்கன்னா x plus 1. So that is the x plus 1 into x cube plus 1. So over any field x cube plus 1 is a factor. Further, if the field contains the primitive cube root unity or characteristic of f equal to not equal to 3. But even without that, they already have the non-trivial factorization x plus 1 into x cube plus 1. So both factors have the degree greater than or equal to 1. So the f of x is reducible over any field f, any field f. So even in characteristic 2, f of x equal to 1 plus x cube plus x power 4. So the in field f2, 1 equal to minus 1 and x plus 1 equal to x minus 1. So therefore x plus 1 something equal to f of x, that is called the reducible. So f of x is never reducible in any field, irreducible in never irreducible in any field. The same way the polynomial f of x equal to x power 4 plus 2x So prove that the polynomial so x power 4 plus 2x plus 2 is irreducible over the field of rational numbers, over the field of rational numbers. So when you use the Eisenstein's criterion, the prime p equal to 2 divides the all coefficients except the leading coefficients. That coefficients are 1 0 0 2 2 2, that is the order I edited now. And 2 divides the 0 0 2 2 and 2 square doesn't divide the 2 square equal to 4 doesn't divide the constant term 2. So Einstein criterion apply panningana with p equal to 2, f of x is irreducible over q, irreducible over q. Okay, so that is very important criterion, Einstein criterion. And f is a finite field. Its characteristic must be prime number. F is finite field. Its characteristic must be prime number p, and f contains the p power n elements of some integers. So then a belongs to f. If a belongs to f, then a power p power n equal to a power p power n equal to a. It's also very important. So for the finite field, characteristic is the prime number, contains the p power n elements of some integers, then a belongs to f, then a power p power n equal to a. And non-zero ideal in a Cartesian Gaussian integers must contain the some positive integer, and R is a ring in which a power 4 equal to a power 4 equal to a, every a belongs to R, then R must be commutative. It'll be easiest to prove. Okay, when I CSIR NET எடுக்கும்பொழுது எல்லாத்தையுமே டிஸ்கஸ் பண்ணுவோம், செப்பரேட்டாக கிளாஸ் போகும்பொழுது. This is R and R dash be a ring and pi a mapping from R into R dash satisfying the pi of x plus y equal to pi of x plus pi of y. Every x comma y belongs to R. Pi of xy equal to pi of x and pi of y, or pi of y into pi of x. So R and R dash is the ring and pi is the mapping from R into R dash, that is satisfying the two condition. Then for all a comma b belongs to R, pi of a b equal to pi of a into pi of b. For all a comma b belongs to R, pi of a b equal to pi of b into pi of a. So then the R is commutative, they satisfy that ring with unit element, satisfy the ab whole square equal to a square b square, R means be commutative. And R be the ring or be the ring of 2 by 2 upper triangular matrices over the field. Example வந்து F2 upper triangular matrix na diagonal க்கு மேல value இருக்கும்னு அர்த்தம். Matrices of the form aduna strictly upper triangular matrices na diagonal is 0. வெறும் upper triangular matrix na diagonal ல some value இருக்கும். So this is the but that is commutative, the product along 0, that is the idea. So given example of the commutative ring with unit element, without unit element, in AB whole square equal to A square B square for all elements of A comma B T, this is a example like that. So like that. So let's connect on. So this is the constructed polynomial q of x with integer coefficients which has no rational roots but is such that for any prime p, solve the congruence q of x congruent to 0 modulo p in integers. That type of polynomials, the q of x with no rational root, with no rational roots for every prime p that is congruent to 0 as integer solution. So that is in the form of like this. Okay. So actually ring theory பொறுத்த மட்டும் I thought field கொஞ்சம் ஸ்ட்ராங்காக பார்த்துங்க, ஏன்னா உங்களுக்கு ஃபீல்டும் சிலபஸில் இருக்குன்னு நினைக்கிறேன். ஃபீல்டு அண்ட் பாலினாமியல் ரிங்ஸ் ரெண்டுமே முக்கியமான கான்செப்ட். ஸோ ஓவராலாக பாருங்கள். ப்ளஸ் ரொம்ப ஸ்ட்ராங்காக பார்க்க வேண்டியது பாலினாமியல் ரிங்ஸ் அண்ட் ஃபீல்டு.